Hello friends, welcome to my channel. In this video I will cover ISRO 2017 paper. These videos are also very useful for IAS, GATE and upcoming RINL MT exam. Question is, a radiator on a space capsule must dissipate heat generated inside the capsule by radiating it into space, while on the bright side of Earth the capsule sees the Earth is radiation and the solar radiation. The radiator surface has a solar absorptivity of 0.5 and an emissivity of 0.9. What is the maximum equilibrium surface temperature of the radiator if the maximum heat generated in the capsule is 800 watt per meter square? Assume Earth's radiation equal to 100 watt per meter square and solar irradiation equal to 524 watt per meter square. Take Stefan Boltzmann constant as 5 into 10 to the power minus 8 watt per meter square Kelvin. Kelvin to the power 4. Let this is the capsule and solar irradiation is 524 watt per meter square, and from Earth's radiation it's getting heat 100 watt per meter square. We have to calculate Q total to the outside from the capsule. Absorptivity alpha equal to 0.5 and emissivity it's 0.9. Stefan Boltzmann constant sigma equal to 5 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. So Q total we have to calculate. Q total is emissivity into sigma Ts to the power 4. Heat also generating inside the capsule, it's 800 watt per meter square. 800 watt per meter square, it's equal to we have to calculate surface temperature Ts. We have to calculate QA equal to emissivity into sigma into Ts to the power 4. This is equal to total heat is 0.5, absorptivity into irradiation is 524 plus then 100 from Earth it's getting 100 plus heat generated it's 800. It's equal to emissivity equal to 0.9 into sigma 5 divided by 10 to the power 8. Ts is, we have to calculate Ts to the power 4. Then you solve this one, you will get your answer. If we solve this one, we will get around Ts equal to 400 Kelvin. From option, our options are in degree Celsius, so 400 minus 273, 127 degrees Celsius. This is our answer. So heat incoming and heat generating, it's equal to Q total. Question is, for profile controls datum is allowed but not required. A is the answer. Question is, a packed bed of solid spheres acts as thermal energy storage system. In charging process, heat transfer from the hot gas increases thermal energy stored within the spheres. Consider two beds, one with aluminum sphere, rho equal to 2700 kg per meter cube, C equal to 950 joule per kg Kelvin, K equal to thermal conductivity K, 240 watt per meter Kelvin, and other with copper sphere. For copper also data is given. Select the correct graph for the temperature rise of the sphere at the inlet of the bed. Here we will use thermal diffusivity formula. Thermal diffusivity equal to heat conducted divided by heat stored. It's mathematically it's alpha equal to K by rho C. Alpha is thermal diffusivity. Alpha represents propagation of heat into the medium, and rho C, its heat capacity, represents amount of heat stored per unit volume. So from data we have to calculate. So if you calculate from data, we will get heat stored in aluminum, it's greater than heat stored in copper. And K value also we have to consider. So from all the data, heat conducted in aluminum is less than heat conducted in copper. And one more thing is important here. From the data we will get alpha of aluminum, its thermal diffusivity of aluminum is less than thermal diffusivity of. So here copper is above, so this is not possible. C, D also not possible. First is, this is the correct graph. A is the answer. Compressive residual stresses in weld joints decreases tensile strength, no. Increases cracking tendency, no. Increases fatigue strength, this is the answer. Sometimes after welding we are giving hammering. So after hammering, in hammering we are giving compressive residual stresses. So it increases fatigue strength. Question is, a force P is applied at a distance x from the end of the beam as shown in the figure. What would be value of x so that the displacement at A is equal to 0? So take the points as O, A, B and this point as C and resolve the force P at point A. Then displacement, you check, displacement at A should be 0. Let BC length is, this is total is 2L, BC is 2L minus X. For BC, your P is the load, resolve it, you will get one moment and one load, 1 point load. So moment is M equal to P into distance is 2L minus X and load is, it's P. This is for BC. At C point, from this P load and this P load, you will get one anti-clockwise moment. This is anti-clockwise and one load P, 1 point load P. For a AB member also we will get one moment and one load. Load is P, moment value is same, P into 2L minus X. Then we have to consider AO. AO distance is 2L, we will get one moment like this. Moment value same, P into 2L minus X and you will get one load like P. We have to calculate at A point deflection is 0. So delta at A point it's equal to 0. So delta at A equal to, it will be 0 if upward displacement due to P load it's equal to downward displacement due to moment M. If both are same, then delta at A point it will be 0. So for moment we will calculate, then for load P we will calculate, we will get our value, X value. This is just like cantilever. So first delta A upwards due to this point load P, it's, we know, P into length Q divided by 3EI. P load is P, length is 2L, it's Q divided by 3EI. This is upward. And delta A downward, it's due to the moment, and we know it's moment into length square divided by 2EI. Here length is 2L. Moment value we will put P into 2L minus X into length is 2L square, then 2EI. Let this is equation 1, this is equation 2. And equation 1 equal to equation 2 for our condition displacement at A equal to 0. So delta A upwards it's equal to delta A downward. This is our given condition. Then cancel P, EI also cancel. It's 8 LQ divided by 3 equal to, it's 4 LQ minus, sorry, this is 2L minus X into 4L square divided by 2, then 8 into 2, 16 LQ, 3 into 8 LQ minus 4X L square. Then take L square common, 16L square equal to 3 into L square into 8L minus 4X, cancel. 16L equal to 24L minus 4X, 4X equal to 24L minus 16L, it's equal to 8L, it's 12X, this is 12X equal to 8L, so X equal to 8 by 12L, 2 by 3 L, 2 by 3 0.66 L. So from option we have to check. From option D is our answer. Question is, an electric heater is sandwiched between two plates, each 0.3 meter long and 0.1 meter wide, with a thickness of 30 mm. At steady state condition, the heater is maintained at a temperature of 100 degrees Celsius with a current of 0.25 amps and voltage of 200 volt. Assume the plates are perfectly insulated at the edges and the heater is having perfect contact with the plates to give a temperature of 50 degrees Celsius on the outside of the plate surface. What is the thermal conductivity of the plate material? So heater is sandwiched between two plates. Let at middle the heater is available. Here let this is the heater. Two plates given. Thickness is X. Here plates to give temperature of 50 degrees Celsius. Both sides 50 degrees Celsius. Inside 100 degrees Celsius. So this area is 100 degrees Celsius. Thermal conductivity we have to calculate. Q equal to K delta T by delta X. So heat generated is V into I. V given, voltage is 200 into I is 0.25, it's 50 watt. Heater is maintained at 100 degrees Celsius, so heat generated equal to heat dissipated. So both sides it's going, the heat is going, so 50 by 2 equal to K into K, area is 0.3 into width is 0.1, K delta T is 100 minus outside is 50. Thickness value it's 30 mm, so 30 divided by 1000. We have to find out the K value. This K value we have to find out. Multiply 100 here, 3 and 1, then 3 0 here, 2 0 1 0 cancel, 3 3 cancel, 50 50 also you can cancel. It's 1 by 2 or 0.5. Unit is watt per meter Kelvin. So from option we have to check 0.5 watt per meter Kelvin. Knife line or hairline cracking is observed in ferritic stainless steel cracking. So ferritic not possible. Martensitic stainless steel, austenitic stainless steel and stabilized stainless steel. Answer is stabilized stainless steel. Riser is designed so as to a freeze after the casting freezes, freeze before the casting freezes, no. Freeze at the same time as the casting, no. Minimize the time of pouring, no. Freeze after the casting freezes. Question is, a torque T is applied at the free end of a stepped rod of circular cross sections as shown in the figure. The shear modulus of the material of the rod is G. The expression for diameter D to produce an angular twist theta at the free end is how much? So here this is the free end theta value we have to calculate. Sorry, this is the fixed end. Free end is here, this side. At free end torque is applied, already mentioned. So here theta value we have to calculate. Our formula is T by J equal to G theta by L into tau S by R. This formula we will use here. Theta equal to TL by GJ. So this is series connection of shaft. T equal to T1 equal to T2. Theta equal to theta 1 plus theta 2. This is section 1 and this is section 2. Then theta 1 and theta 2 value we will put T1 L1 by G1 J1 plus T2 L2 divided by G2 J2. J value is changed, G value is same, modulus of rigidity G is same, torque also same torque, both section 1 and 2. Then length is changing, T into L by G1 J1 is 5 by 32 D to the power 4. For second section, length is T into L by 2 divided by G2 is G into 5 by 32, it's 2D. So 2 to the power 4 it's 16 D to the power 4. Take common TL by G pi D to the power 4, take common. We will get 32 here, 32 plus 1 by 2 into 32 by 16. 2 cancel, 32 plus 1 TL G pi D to the power 4, it's 33. We have to calculate D value. So for D to the power 4 it's TL G pi theta 33 whole to the power 1 by 4. This is for D value. This is our answer. Answer is B. This is series condition. So you have to remember series formula, shaft in series, T value and theta value, and this formula also you have to remember. Thank you friends. Thank you for watching my video. Thank you.